Okay. So you have assignment 4. Assignment 4 is due on Monday. Figured I could push it a little bit. My 1-week rule. Wednesday to Monday isn't that bad, and it's only 1 page. Well, double-sided, but still. And I think you could probably kind of crank it out in not that long at all. For question 1, part A, that's from chapter 3, okay? And then the rest of the parts, so B and C from question 1 and all of question 2, those are from chapter 4. Okay? So just a heads up. Wait. Okay. So let's do a little bit of, won't review too much because it was just on Monday. But we were talking about hypothesis testing, right? Which is kind of a big thing that we have to do. But as we do more and more of it, and you'll do it on question 2 on the assignment. So as you do more of it, you'll start to get the hang of it, and then it'll be fine. Okay. So here I'll put a little start on confidence intervals. Oops. But as far as hypothesis testing goes, right, we're going to follow these 4 steps. So the first step is to state our null and alternative hypotheses, right, H0 and HA. And then we're going to do the test, which means calculate a Z-score, essentially, right? And then step 3, we have to find the p-value. What's the probability of observing this, this sample mean if the hypothesized mean is true? And then we draw our conclusion based off of that, right? And so we said that this is kind of like this big concept that we have. So if the p-value is small enough, right, smaller than the alpha level, the default alpha level is 0.05, then we have enough evidence to reject H0, right? If it's not smaller than the alpha level, then we don't have enough evidence to reject H0. Right? And so we always draw our conclusion in terms of the null hypothesis, right? And that's because we do all our testing assuming that the null hypothesis is true. Okay? So we said there were 2 main ways that we can test a hypothesis, right? Or for inference in general. We've talked about hypothesis testing. Today we're going to talk about confidence intervals. I find that people like confidence intervals more, so that's why I like to start with hypothesis testing and then go into confidence intervals. Okay. So the difference between the 2 is that hypothesis testing, it tells us if something is significantly different from a hypothesized value, right? So is it different or is it not different, right? Whereas confidence intervals tell us how different things are, right? So a confidence interval gives us an idea of a range of plausible values that the population mean could take on. Okay? And so it's kind of like if I said, oh, how far is it to that blackboard, right? I would give an estimate, right? The estimate would be the same as our sample mean, right? That's our best guess at what the population mean might be, right? The sample mean is the estimate of the population mean. But we know that even if I say, okay, I think it's, I don't know, I'm terrible at distances, so I shouldn't have done that actually. I don't know, 5, 6, 5 to, well, I guess this is a good example. 7 meters, I don't know. Is that reasonable for me to the blackboard? Diagonal? Tough call. My best guess is 7 meters, right? But because I'm not sure, right, of my estimate, that's my best guess. right? That's what I was willing to put out there, right? So that's your sample mean, okay? But then usually what we would do is we would say plus or minus 2 meters. I'm not that confident, right? And so now I've built this interval of values that I think might capture the actual distance from me to the blackboard, right? And so that's what we're doing with confidence intervals, is we know our sample mean isn't going to be exactly the population mean, right? But it is our best guess, right? And so what we're doing here is we do a little plus minus calculation to get an interval of values that we are some percentage confident is going to capture the population mean, right? And so here, we've seen X bar before, right? That's our sample mean. And then plus minus is fine. Z star is a critical value. Okay? So Z star, we actually find, and I think I've shown it to you briefly before, Z star is confusingly in the T table. So if you have your table, or if you want to borrow a table, or if you've lost your table, you can come grab one. But if you go to your T table, actually, I'll see if I can pull it up here. When was that? I have it here. Okay. So our T table looks like this. So we have these confidence levels. And I'll only ask you to build confidence intervals at those levels. Okay, so I'm not going to make you do anything weird. Because the follow-up question would be, okay, so my best guess is 7 meters plus or minus 2 meters. And then you would say, well, how confident are you? 95% confident is what I would say, right? Because there's a chance that my interval didn't capture it, right? If I said something like 7 meters plus or minus 10 meters, how confident am I? I'm really confident, 99% confident. We can't do 100% confidence interval because I would have to say something silly like, oh, it's 7 meters plus or minus 1 kilometer. I'd be 100% confident, but it doesn't tell me anything, right? And so we use these confidence levels. Okay, so what you're going to do is, if we're building a 95% confidence interval, for example, we need the critical value for that. Okay? So you go to 95%, and then you scroll down to the bottom. And 1.96. If you think about the 68, 95, 99.7 rule, right, then we were expecting to have a critical value of 2, right? So what's the deal? 1.96, that's pretty close to 2, right? It's just a more precise version of it, right? So we're going to use 1.96 because we have that precision, so why not use it, right? But the idea is the same. So we've moved out 2 standard deviations, right, or 2 standard errors from the hypothesized, from the sample mean, sorry. So that's where the Z star comes from. Sometimes I see people trying to use a calculated Z, right? But the star is the giveaway that says, no, this is just a value from a table. So let's make a little note here. Found in T table. In the list below it. Good to emphasize. And then we have sigma over root n, right? Sigma over root n, remember, is the standard error, right? And so before, with the 68, 95, 99.7 rule, right, we were saying, okay, well, if we move out 1 standard deviation, 2 standard deviations, right? All we're doing now is we're saying, okay, we don't have these standard deviations, but we do have standard errors for X And so now we're moving out essentially 2 standard errors around the sample mean. Okay. And then, so here, I've got them listed, but let's just say X bar plus minus, you know what, I'm gonna make a smaller size pencil. Pen, maybe. X bar plus minus Z star times sigma over root n. Just because there's a lot of terminology around this. Okay. So Z star is the critical value. Sigma over root n is the standard error. And then the final point that I've got there is that this whole chunk is called the margin of error. And I emphasize that because we'll use it later on when we're trying to figure out what sample size we need. Okay. So on the side here, I've got, because we know, already told you, right, that we're going to move away from Z's and move into T's, right? But a confidence interval with a T looks essentially the same, right? We've still got our estimate. We've got our critical value T star, which you find the same way, just different spot in the table. Okay. And then the difference between T and Z is that we use the sample standard deviation instead of the population standard deviation, and then over root n. But all the terminology is the same, right? We've got the critical value, the standard error, and the margin of error. So it doesn't matter which confidence interval we're talking about, right? But for now, we're just talking about this Z confidence interval. Any questions? So here I've got a little description on how to find Z star. Okay. And then just some quick exercises. Right. What's the Z star for a 90% confidence interval? Just to practice. Let's see here. So a 90% confidence interval, I find 1.645. So Z star is 1.645. We already found the Z star for a 95% confidence interval, 1.96. 0, I guess, to be consistent. And then we can look up for a 99% confidence interval. 99 gets a little tricky because there's a lot of 90s here. 2.576. So that's how you're going to find your critical values. Okay. Which is really the only kind of new part for confidence intervals, right? And so I've got the little point about connecting it to the 68, 95, 99.7 rule, right? One thing that I do want to note, right, is the notation. So once you've found your interval, right, for example, going back to my kind of fake example of the distance from me to the blackboard, 7 meters plus or minus 2 meters, right, that's going to give me an interval from 5 to 9 meters, right? And so how you're going to write those is in round brackets, and then 5, that's my lower estimate, right, comma, 9, and then end bracket. And so the notation here is really important. So just do as I say. That's all I can say. As a default, so we always have these defaults. As a default, we do 95% confidence intervals. Of course, in this course, for testing purposes, I'll say make a 90% confidence interval, make a 99% confidence interval, right? Again, there'll always be something with a confidence level on your t-table, right? So I would never make you do anything beyond those, right? Most common ones, 90, 95, I guess maybe 98, 99. I don't really stray from those. But it doesn't matter, as long as you know how to find the critical values, everything else is the same. Okay? So as a default, we use 95% confidence intervals. So if you're reading a research paper, for example, it's very likely that they're using 95% confidence intervals. Okay? Unless there's something they don't want you to know about, then they might use a 90% confidence interval or a 99% confidence interval, depending on what they don't want to show you. Default 95% confidence interval. Okay? And so like I said, the reason we don't make 100% confidence intervals is because our bounds, right, our upper and lower bounds would have to be so wide that it's not really helpful anymore, right? For us to be 100% confident, right, it just doesn't tell us anything, right? And so the 95% confidence interval is the trade-off between still being confident, 95% is still confident, right? And precision, right? Precision is how tight are our bounds on our estimate. Okay? So that's the reason. There's also a link. Remember from last day, we said the default alpha level is 0.05. And so I'm going to say here with a two-sided, because going back to the defaults for an alpha level, right? For the hypothesis test, with the default is a two-sided test, right? Not equal to, and then the alpha level is 0.05. Right? So what does that look like? It looks like this. Here and here, two-sided, 0.05 means that we have 0.025 here in the tail and 0.025 here in the tail, and 0.95 in the middle. Clean that up. So here's our two-sided alpha level of 0.05 and how it connects to a confidence interval or a confidence level of 0.95. Oops. And I'm pretty sure, yeah, you have to do one for question 2, part B on the assignment. I've got this kind of cryptic. Use a confidence interval equivalent to a one-sided alpha level of 0.05 for the house prices today. So what changes here for that question? Well, now in one side, you've got 0.05, right? But because confidence intervals are still intervals, right? Now you've got 0.05 here and 0.05 here. So what confidence interval am I asking for? Right? 0.05 here, 0.05 here. I'm asking for a 90% confidence interval. Maybe jot that down. Reverse engineer it later. Okay. So they're definitely linked. Right? And the tricky part with confidence intervals is not the calculation. The calculation you'll find is fine. Okay. It's more the interpretation. So of course we always have to interpret our interval once you've made one. Okay. There are lots of ways that you could misinterpret it. Okay. And so what I would recommend is just until you really have the hang of it, or maybe forever, I don't know, doesn't matter to me, use this sentence structure. Okay. I'll be using this sentence structure very consistently, okay? And it applies to any confidence interval that we make. Okay? And so what we're gonna say, we are 95% confident, for example, okay, that the interval from 5 to 9 meters captures the population mean distance to the blackboard. Doesn't really make sense, but whatever, right? And so I've asked you to make a confidence interval of something, right? So here at the end, you can just reword the question as an answer. Right? Just take what I asked you to make a confidence interval of and plug it in there. So the idea is, or the important part, I should say, is that the population mean is fixed, right? It doesn't move, right? Our sample mean changes depending on our sample, right? And so the most common mistake that people make is trying to tell me that the population mean is changing, right? It's fixed, we don't know what it is. We're trying to capture it, right? And so that's why it's important that you use that the interval from this to this captures the population mean. So here, I guess the population mean, this is going to change, right? Depending on the type of question, what we're talking about, right? But for the first little bit, we'll still be talking about the population mean. So the interpretation is the same for whatever type of confidence interval you've made. Okay. Let's do the example. Okay. So it's the same example. I've just kind of emphasized it, and then here at the end, I've got construct a 95% confidence interval for the mean odor threshold of all wine tasters. So we've got the information here, and then we're going to make a 95% confidence interval. I'll do that down below. Down here. Example 5. We'll list the information that we have. Oh, there. So we know, so we've been given X bar is 21.5. So it's the same one. This is the same question that we used last day, so boring, I know. X bar is 21.5. Sigma is 7. N is 30. And if we just think about the formula for the confidence interval, right, we've got X bar plus minus Z star times sigma over root N. We have X bar, we have sigma, and we have N. Notice that mu doesn't come into it, right? Because for a confidence interval, you're trying to figure out the range of values that might capture mu, right? So mu has no place here. Okay? The last thing that we need is your Z star. Right? So I'm just going to jot it down here. And even if you just say Z star is, so we've got a 95% confidence interval going down to Z star, you've got 1.960. From the t-table. So as long as you write something like that where you just tell me what it is, tell me where you got it from, that's good enough. So let's plug all these values in and see what's going on. So we've got 21.5. That's our sample mean. So that's our best guess at the odor threshold for wine tasters. Plus minus Z star, which is 1.960, times sigma, which is 7, over the square root of N, which is 30. Definitely for confidence intervals, you'll want to figure out how to store values on your calculator. It'll just make it easier. Okay? So if you have a store button, I can help you find it. If not, it's no big deal. But yeah, so if you want me to help you find the store button, we can do that after class. So we've got 21.5 plus minus, and then I'll just do these step by step. 1.960 times 7 divided by the square root of 30 is 1.278019301. Times 1.96. So now we've got plus minus 2.50491783. So I'm going to store this value in one. And then how I'm going to write out the answer. One trick that you can use is to look at the information that I've given you. Okay? And because I didn't tell you how many decimal places to give me, right? But one trick that you can use is, this is all the information that I've given you, right? The highest number of decimal places that I've given you is 1. So you just have to match that. Okay? And so just as a quick rule of thumb, just match my decimal places. You don't have to go more than that. Okay? So, but because the decimal places could change depending on what all these values are, you still have to keep them until the end, right? You can't round until the very end. So we've got an interval, and how you're going to write it, right, is start with a round bracket, and then you calculate your lower bound, 21.5 minus 2.50491783. My lower bound is 18.99, I guess I'll show you, 508 0.6217. Things got dicey. If you wanted to round it right away, that's fine. But because I have it, I'll just do all of them. 21.5 plus, to get my upper bound, 2.5049 is 24.00491783. Or 19.0 to 24.0, rounding to 2 decimal places. 1 decimal place. So used to 2. Feels like cheating with 1. So that's how you're going to find your interval. Right? That's half of the work. The rest of the work is interpreting this interval, right? What does this interval mean? So this is where we apply that sentence structure that I showed you. Okay? So we're going to say we made a 95% confidence interval. So we are 95% confident the interval from 19.0 to 24.0 captures, and then if you refer to the question, I asked you to construct a 95% confidence interval for the mean odor threshold of all wine tasters. Right. So I'm just going to steal that, captures the mean odor threshold for all wine tasters. So captures the mean odor threshold for all wine tasters. Yeah. I know on the test, I'll tell you how many decimal places. So if it is 1 decimal place that I want, then yeah, you have to give the 0. Because 19 is actually not the same as 19.0. I know, weird. So, better than hypothesis testing, I think, right? Not as many rules, not as many ins and outs, okay? How about this? We can use a confidence interval to test a hypothesis. Perfectly reasonable, because what we're saying here is I'm 95% confident that the mean, the population mean, or you could say the hypothesized mean, is somewhere in between here and here, right? So if you kind of flip that and say, okay, well, the population mean for wine tasters is between 19 and 24, right? So what you're going to do is you're going to check, well, is my hypothesized mean in there? No, right? Because our hypothesized mean was 25, right? And so here, 19 to 24, both of those are below 25. So then you can reject the null hypothesis that the mean for wine tasters is 25, right? Because you're 95% confident that the mean for wine tasters is between 19 and 24. Right? And so you can use a confidence interval to draw a conclusion. So here, using the confidence interval, we can test a hypothesis. Say we want to test that same hypothesis, H naught is that mu is equal to 25. And then we had HA that mu is less than 25, right? We suspect that their odor threshold is less than the general population. So now, right, we can say, okay, well, looking at this here, my mean, my hypothesized mean is 25. Right? So what I'm going to say is using the confidence interval, we are 95% confident the population mean for wine tasters is captured between 19.0 and 24.0. What I'm going to argue is that's consistently, both of those bounds are consistently below 25. Okay. Which are consistently below the hypothesized mean of 25, below the hypothesized mean of 25. So we have enough evidence to reject the null hypothesis. So we have enough evidence to reject H naught in favor of HA. That mu is less than 25, right? Which is confirmed by the interval being between 19 and 24. Somewhere in there, we're 95% confident that we'll find our population mean. So we can do hypothesis testing in either case, right? I'll call the normal, the 4-step process, that long question. That's a formal hypothesis test, right? And then we can test it with a confidence interval if we want to. So, any questions about that? Oh. So, there's kind of 2 more things. There's one thing I forgot to put in the notes, but it's just really brief. So the next thing we're going to talk about is calculating the required sample size. So it's not very realistic that you know sigma, but if you do, if you happen to know sigma, the population standard deviation, then you can go ahead and figure out how big of a sample size would you need to get some desired margin of error. Okay? The reason that I'm introducing this is not so much for when you know sigma, but later on, when we want to estimate proportions instead, then it's more likely that you have to calculate the sample size. So we're going to do it for both scenarios just because we can, right? But the one for proportions is more applicable. Okay? So calculating the required sample size, where was it here? Got it up above. So sigma, so that's a key part. And a desired confidence level, Z star, right? So if I said, okay, you want to be 90% confident with a margin of error of 3, right? I'm not sure what that is, but then you can find, and the standard deviation is 4, let's say, then you can find the sample size that you would need to make that happen. Let's do the example instead. So if we want to decrease our margin of error to plus or minus 2, and this is in reference to the other question, right? We had a sample size of 30, right? We had a sample size of 30. Okay? And let's just have a look here. The margin of error is this chunk, right? So our margin of error in this problem was 2.50491783. Right? So our margin of error right now is 2.5. Okay? We want to decrease that margin of error to just 2. How big of a sample size would we need to make that happen? And I think the confidence level is the same, yeah, 95%. So example 6. I'll just make a note here. Our margin of error with n equal to 30 wine tasters is, I'll steal this. It's because I can't memorize and scroll. I'll put in brackets around 2.5. How many wine tasters would we need to sample to decrease our margin of error to 2? So I'm just going to write out the formula for the confidence interval so we can have a look at it. X bar plus minus Z star times sigma over root n. This here is the margin of error, right? Let's call it lowercase m. Right. Some textbooks call it capital M-E, capital M, lowercase m. It doesn't matter, M-E, M. So m is Z star times sigma over root n. And just because we're doing calculations now, I'll write it like this. Solving for n, trying to solve for n here, and don't worry, it's on your formula sheet, the formula that's on your, in the notes, right? I'm just showing you how we got there. Okay. So now we've got m is Z star times sigma over root n. First thing I would do is I would multiply both sides by the square root of n. So we get m square root of n is Z star times sigma. Trying to get n on its own, we're going to divide both sides by m. Square root of n is z star times sigma over m. And then to try to get rid of that square root, we have to square both sides. So n is z star times sigma over m, all squared. Well, looks like a z. Okay. This is on your formula sheet. So don't worry about deriving it, but that's where it came from. So it's not that crazy. So now if we want to solve for n, so in our case, z star is 1.960 because we want a 95% confidence interval still, right? Sigma is 7, and m, our desired margin of error, is 2. Let's make a note of that. Desired margin of error. So if we calculate n is z star times sigma over m all squared. Oops. It's going to be 1.960 times 7 over 2 to the power of 2. 1.96 times 7, I'll just divide it by 2. 6.86 squared. My squared keeps looking bad. There. So square that. I get an n of 47.0596. We need to sample 47.0596 wine tasters. Tricky part is we can't get 0.0596 of a wine taster, right? And so even though this is really small, if we only sampled 47 wine tasters, the way that the n works in our equation, we actually would have a slightly larger margin of error than 2. Right? And so what we always have to do is we always have to round up to the nearest whole number. So we would need to sample 48 wine tasters to get the margin of error down to 2. It's going to be a little bit less than 2 even. So since we can't sample 0.0596 of a wine taster, we must round up to the nearest whole value. So we would need n equal to 48 wine tasters. Any questions about that? Okay. So the last thing that I want to talk about is decision errors. So in hypothesis testing especially, right, there's always a chance that we're wrong, right? And so decision errors not in printout, just as a note. Okay. So decision errors are if we say we reject the null hypothesis when we shouldn't, right? Or maybe we don't reject the null hypothesis test when we should. Trying to think it out, okay? And so in hypothesis testing, there is always a chance that we make a decision error. So usually how this is communicated is in a table. And so it's going to look something like you've got your test conclusion up top, and then you've got the truth, or kind of the in quotes truth. Well, I guess it is the truth. We'll never know what it is. That's the problem. Right? If we knew the truth, we wouldn't have to do any testing. Okay. So our test conclusion, we can either reject the null hypothesis or we don't reject the null hypothesis. Right? So here we've got do not reject H naught, or here we reject H naught. The truth could be that H naught is true, or H naught is false. So we've got this kind of situation. If H naught is true, and you decide that you're not going to reject it, that's okay, right? That's not an error. It's all fine, right? So this one is okay. If you decide to reject H naught, so you're rejecting it, you're going with HA instead, when H naught is actually true, that's going to be called a type 1 error. Okay? So type 1 error. The type 1 error, wish I had more room on the side there. Type 1 error is the p-value, right? The probability of making a type 1 error is the p-value. Right? There's always a chance that even though it's small, that H naught is true. Okay? So the type 1 error happens with a probability equal to the p-value. If you decide that you're not going to reject H naught, when H naught is false, that's also an error, right? And that's what we call a type 2 error. Type 2 errors are harder to kind of quantify, right? You definitely can, but beyond the scope of this course. Type 2 error. And then finally, if you decide you're going to reject H naught when H naught is false, that's okay, right? Because that's good. That's basically all I wanted to say about it. Any questions about that? Yeah. Oh, which one?
There's always a
Chance.
chance.
Oh, there. There's always a chance. It's like Dumb and Dumber. It's like, you guys seen Dumb and Dumber? Is it too old? Okay. Anyways, she's like, or what is it he says?
In a million years, I think.
Yeah, he's like, what are the odds of us going on a date? And she says, about 1 in a million. And he gets all excited. He's like, so you're saying I've got a chance? So that's what p-values are. There's always a chance. At least someone's seen Dumb and Dumber in here. Any questions? No? So I don't know, we just kind of plowed through that. You can take this time to work on the assignment or do whatever you want. Oh, I will show you just briefly here. On Moodle, I've posted all these practice problems, right, with solutions. I haven't revisited the solutions in a little bit, so there might be some errors. If you come across something that doesn't seem to make sense, then just let me know. Okay, but the chapter 4 practice questions, I haven't really pointed you in the direction of the practice problems until now, but starting at chapter 4 and moving onwards, they're solid. Okay? So definitely for practice, especially because you have, so I don't really care about the textbook questions. I just gave them to you so you could have them if you wanted to. But as far as practicing for a test goes, then all these questions that I've typed out are good. One thing to keep in mind is that these practice questions could be a little bit trickier than what I would expect from you on a test, right? Because you have all your resources, you can Google things, you can look through your notes, whereas on a test, you don't have those things available, right? And so these are kind of to broaden your mind, let's say. Okay? So have a look at the practice questions for chapter 4. Any questions? No? The time is yours. And you've got assignment 4 and it's due on Monday, not Wednesday like I usually do.